Hi everyone, and thank you for attending our presentation on Serenity, a distributed security policy management and enforcement system for smart homes. My name is Corentin, and I just graduated from Polytechnique Montreal. This project was supervised by David Barrera. Consumer IoT devices often make the news, and not for the best. As it turns out, we can't really trust them. In fact, Avast estimates that roughly 40% of smart homes globally have at least one vulnerable device. These vulnerable devices expose the privacy and the physical security of their owners and can allow attackers to access sensitive data, as in the case of smart cameras, or to break into smart homes by attacking smart locks. They are also a threat to computer systems and internet infrastructures, as shown by the various botnet attacks in the last few years. To mitigate these risks and help users feel safer around their smart things, we worked on Serenity, a distributed security policy management and enforcement system for smart homes. The goal of Serenity is to protect smart homes and consumer IoT against device hijacking. It's tailored for smart home use and to require little to no interaction from the end user. Serenity has also been designed to be independent from manufacturers and to be backward and forward compatible with TCP/IP IoT devices. To achieve these goals and build security policies, Serenity monitors the behavior of a large number of similar IoT devices in multiple smart homes. To do so, Serenity relies on middle boxes called sentinels. Sentinels monitor the device's network traffic to build the security policy and block anomalous packets. One sentinel is deployed per smart home. Sentinels are directly integrated inside the home network and sit in between the IoT devices and the home router, allowing them to record all the device's network traffic. Sentinels collaborate and report behaviors they record for the devices they protect. These reports are aggregated to build a decentralized security policy. The behaviors recorded by a majority of sentinels are trusted, and the behaviors recorded by a minority are flagged as anomalous and are blocked by the sentinels. This mechanism allows to block attacks and to keep the security policy up to date during all the lifespan of the IoT devices. This mechanism relies on three key aspects. First, the sentinels that are collaborating to build the security policies. One sentinel is deployed per smart home. Second, the blockchain, which provides the decentralized ledger used to record the sentinel's observations and build the security policies. And third, the allow list, which is the security policy and which lists the packet signatures corresponding to the trusted behaviors. The Sentinel workflow is pretty simple. When they intercept a packet from an IoT device, they compute its signature and check the security policy to verify if the signature is trusted. If that's the case, the packet is forwarded. Else, the packet is dropped and reported to the decentralized ledger. The packet signature algorithm, which we use, allows sentinels to identify the distant host and the service port used. We discuss in more details the packet signature algorithm and the possible improvement in the paper. As I mentioned previously, signatures reported by sentinels are recorded in the blockchain. The longest chain contains the signatures reported by a majority of sentinels and corresponds to the security policy for a device. The signatures listed in the longest chain are considered trusted. In the paper, we also detail how the system deals with signatures reported by a majority of sentinels. To evaluate our solution, we have set up two experiments. The first one, with real IoT devices, is meant to evaluate the behavior of Serenity in a small-scale network with real IoT devices. Here is a picture of the test bench used for this experiment. On the left, we can see the 3 leafy smart bulbs used, as well as the 3 Raspberry Pis running the Sentinel software. This graph represents the number of packets recorded by the Sentinels and the corresponding signatures during the 4 first minutes following the bulb's first power on. We observe that around 2 minutes and a half, the security policy contained 2 signatures. This shows that a security policy has been correctly built and that the system works correctly in this setup. To evaluate our system with a larger number of devices, we have also set up a large-scale simulation in the cloud with up to 1,000 Sentinels and 53 different IoT devices types simulated from the Harari and HAL dataset. By analyzing the dataset, we observed that the number of unique signatures per IoT device remained small over the 10 days period covered by the dataset. In the paper, we also discuss what kind of devices falls under this category. Here is a little demo of a simulation. This demo experiment uses 20 Sentinels and 3 different IoT devices simulated from the Harari and HAL dataset. Blockchain storing the security policies of protected devices can be accessed by clicking on the blockchain card on the right. This view represents, for example, the blockchain storing the security policies for leafy smart bulbs. By clicking on the Sentinel on the left, we can access the packet filter view. The packet filter view shows the rules applied by the Sentinels to filter the network traffic of the IoT devices. Let's simulate an attack and click on the attack button. It's going to simulate an HTTP port scan on port 80, 8080, and 443 on this device, similarly as a botnet will do during the recon phase. When we click on the attack button, the injected traffic is blocked by the Sentinels. Let's proceed and simulate the same attack on 2 other IoT devices. As we can see, the other Sentinels also block the anomalous packet, as the corresponding packet signatures are not listed in the security policy. When we switch back to the blockchain view, we observe that new packet signatures have been recorded to the blockchain. If we wait a few seconds, we can then observe that the blockchain forked and that the anomalous packets corresponding to the simulated attacks were rejected and won't be added to the security policy. The graph on the top represents the consensus of the Sentinels. And as you can see, the signatures have been rejected and all the Sentinels are soon going to agree on the same block. And this concludes our demo. As this demo shows, the Sentinels were able to converge and build security policies for the devices, and they were also able to block the injected anomalous packets. To conclude, Serenity allows to filter anomalous packets from home IoT network traffic. It requires little to no configuration from the end users and it is tailored for home use. It is also fully decentralized and independent from the device's manufacturers and is compatible with a wide range of IoT devices. However, we would like to mention that Serenity has also some limitations. First, the current version only monitors LAN-to-WAN connections. It works best for devices with a small and constant network footprint. Serenity may also block some specific connection while the corresponding signatures are not revealed by a majority of sentinels. And finally, there is a greater chance of abuse when adoption is small. Thank you very much for your attention. This is the end of the presentation. If you have any question, please feel free to ask.